we do, this would not be a major event now, okay? There would not be 9 volts drop available across this resistor. There would only be 4.5. It makes sense conceptually. These positive charges really didn't like hanging out next to each other, and they had a massive energy reward for going into this minus plate, right? Well, now the situation is just not that dire. Instead of having a 9-volt difference across the resistor, it's only 4.5. Because these positive charges, they still repel each other, but they're like, well, I didn't mind these minus guys. I don't want to get out of here so badly now, right? And over here, yes, they still want to join up with these minuses, but they don't want it as bad anymore, because there's also these positive charges here. We've essentially evened things out a little bit, right? Instead of making it hugely desirable to go across the plates, now it's not that desirable. We've reduced the voltage difference. You can also think of it as like, instead of having a big voltage hill and a big voltage valley, we've now kind of filled in, right? This voltage hill is a little bit dug out with the minus charges, and this voltage valley of minus charges is filled in a little bit with plus charges. So the charge polarization has made the energy situation different. Instead of a big energy change, it's a smaller energy change, right? So, does that make the capacitance better? Well, if we look at the fundamental definition of capacitance, we seem to get away with it. C equals Q over V. That's the definition of capacitance, right? Is how much charge you can store per volt of effort. You have a better capacitor when you can store more charge for the same effort, right? Now what's happened in our case is that Q is fixed. We haven't changed the amount of charge that's stored, but we have decreased the voltage difference across the plates. And so technically speaking, we have increased the capacitance. Now you might think that's like a cheat. Is that really better? We haven't stored any more charge. We've quote unquote reduced the effort to do it. But that's just a weird thing, because we really did charge it with a 9-volt battery. We went back after the fact and said, oh, it wasn't really that, we didn't really try that hard. Okay? So it seems like kind of a cheat to say that it's better, right? Is this really better? We're storing the exact same amount of charge, and the effort, quote unquote, that we did this with was reduced after the fact. Okay? But we have to acknowledge the fact that, at least by the equation, it's better. So if this is fixed, and this is reduced by kappa, 1 over kappa, then this is going to result in this being increasing by kappa. So this is increased. Keep up here. So at this point, we've increased the capacitance on a technicality. Nonetheless, since it is increased and it's become part of the physical construction, the last piece that we need to acknowledge is that by the insertion of a capacitor, or sorry, the insertion of a dielectric, we have improved the capacitance. So if you include a dielectric between the plates, you multiply by the dielectric constant. By the way, you will find on your equation sheet a whole table of these. So you can find out, oh, this material has this kappa, this material has this kappa, okay? So at this point, it all seems like a little bit of like, just making it better on a technicality. And when we work out what happens with the energy, we'll really see that it's a technicality. Let's grab one of these energy formulas, okay? So PE equals 1/2 QV, let's say. Now, our initial amount of energy was, of course, based on the initial charge and voltage. Then, after that, we have the same amount of charge but at reduced voltage. So the Q is still the same as we said, same, but this is decreased. So what happens to the amount of energy stored? It decreases, that's right. So the new amount of potential energy, of course, all this stuff is still the old potential energy. So we have the original amount of energy divided by kappa. So at this point, you say, this cannot possibly be better. We're not storing as much energy as we were before. We've calmed the situation down, right? We've basically made the plates closer together in voltage than they were before. This partial shielding leads to the voltage difference in electric field being reduced between the plates. So the two plates are not drastically different in voltage anymore. They're much closer to being similar voltages to each other. And at this point, if you were to question what is the possible utility of doing this, we've increased the capacitance on what seems like a technicality, and we actually have less energy than before. Well, obviously, this is not the end of the road. This right here just gives us an opportunity. This gives us an opportunity to do something. So there's one more step here. Now, what we're going to do is we're going to reconnect the battery. So whatever battery we use to charge up this capacitor, we used, I guess I called it 9 volts before. So we can charge this capacitor with a 9-volt battery. Then we disconnected it and stuck in the dielectric, and the dielectric brought the voltage down to 4.5. Then you bring in the battery back and connect it to the capacitors, and it says, wait a minute. Last time I saw you, I charged you up to 9 volts. What are you doing here at 4.5 volts? I thought I charged you up. And the capacitor says, I'm sorry, I took on this dielectric in between my plates and reduced the voltage difference. And the battery says, hey, that's great, but now you're hanging with the 9-volt battery again. Up, you go back up to 9 volts, right? So that's what happens. Well, to get it back up to 9 volts, despite this thing in the between, which is shielding, you're going to have to put more charge on. Remember, it was full before. Now we get to put more charge back on, okay? So basically what the effect is of the partial shielding is that it suppresses the voltage difference so that you can put way more charge on than you could have otherwise, right? Before, you could only get on so much charge before the voltage across the cap was 9 volts. Now, if you keep that voltage down with that partial shielding, you have to pack on that much more charge to get up to 9 volts. So here's what we're going to find. This is going to increase right back up to the original voltage. Right back up to the same net field. The battery is going to say, you can't be down there. You can't be down at 4.5 volts. When you're attached to this battery, you get up to the same voltage as I am. Okay? So, what happens here? How can you possibly get up to the same net field? So you have, the net field was this size before, so I'll try to draw that. So it used to be like this. This was the net field before you had partial shielding. Then you had, I guess I can draw it below here. That might be easier. I'll draw it. So this was, your net field was like this. Then it was like this. You took some of that off. And that leaves you with a smaller net field. Looks like this. How could you get the net field, which is this? If you're going to get that back up to the same size, well, the only way that's going to happen if you took a chunk of it off was that the plates themselves have a larger field. Okay, so this is E net. So I'll try to draw these. This is, let me try to mark this off so it's clear. Looks like this. So again, just to reiterate, make sure it's clear. Here's how much field the original amount of charge makes. We have that field by those original amount of charges, and then we have the induced field in red taking off some of that, and the net field is smaller, right? That's why this is smaller. Over here, we have to get up to the same net field and the same voltage despite this effect. So the plates themselves are going to have to make a much more larger electric field so that when E induced takes it off, you're back up to this, back down to the same amount as you were initially, right? How is it possible for the plates to make such a big field? They have to take on more charge, right? So we increase the amount of charge. That is the only way we're going to get a stronger net field. And again, we already reasoned that up. We already reasoned that out, right? If you have a 9-volt battery that charges this, and then the dielectric takes the voltage down, the battery's going to get it back up by putting on that much more charge that it couldn't have put on before. Right? I should point out that the capacitance is still the same. It's a function of the physical construction, with the dielectric still in there. So now let's figure it out. Let's figure out what happens here. So we go ahead and we use C equals QV. And let me invert it. So it looks like that. If we go back to the very beginning and index everything from the very beginning, we have this. Now, at the very end, we have that we're back up to the same amount of voltage. The battery is going to force the issue. But we have an increased capacitance, so we're going to have more charge. So we're going to find that if this increases by kappa, this increases by kappa. So this is kappa times Q naught. So here's one way to think of it, right? If the dielectric is going to reduce the voltage by half, you need twice the amount of charge to get back up to the original voltage, right? Does that make sense? The only way you can get up to the same original voltage with a voltage that's being cut by half by the dielectric is to put on twice the amount of charge. Okay? So now we're talking. We have been able to put on way more charge onto this capacitor than we ever could have without the dielectric's assistance. We never could have put this much charge on. If we had tried to put twice the amount of charge originally, that would have made the voltage go up to 18 volts. You can't make a voltage across a capacitor go up to 18 volts with a 9-volt battery. You can't, it's not enough. You can't charge a capacitor to higher voltage than the battery you're using to do it, right? So you would have never gotten this much charge on there in the first place, because that much charge would have made the voltage higher than you had access to. So the cool thing about the dielectric is the fact that it allows you to put the charge on while keeping the voltage down, because as soon as you hit the amount of voltage that the battery has, then you're done charging. So you get to put all this charge that you never could have put on before, right? Because the dielectric keeps the voltage suppressed. Does that make sense? Okay, so let's go ahead and finally figure out the effect of the energy. So the original amount of energy at the very beginning, of course, was this. Now, what we have is the same voltage as at the very beginning. The battery is going to force the issue. But now, we have that the amount of charge is increased by kappa. It took that much more charge to get up to that voltage now because of that suppression we were seeing. So what's going to happen to the energy stored? It's going to increase by kappa, that's right. Now we're talking. We store more energy than we ever could have previously. How is that enabled? It's still the same battery that we connected at the beginning and connected at the end. So it's the same voltage, which means it's the same energy per charge. So if you take a look at any given charge on there, it's got exactly the same energy regardless. The big difference is that we have been able to pack more charges on there. That's the key. So we were able to get 2, 3, 4 times whatever the dielectric is, that much more charge on there for this with the same charging battery. If you put a dielectric in there, the dielectric holds the voltage down. So we have to put 2 times, 3 times, 4 times more charge onto the capacitor before we get up to the charging voltage. That's why you store more energy. You have more charges with the same voltage. So this, of course, is why we use dielectrics. They allow you to store more charge and more energy on a given voltage. Okay? So you can store far more things on there than you otherwise could have. You store more charges, and they have more collective energy stored. So, a couple things about this. First of all, if you're interested in storing more charge and more potential energy, why don't you just use a larger battery to charge these in the first place, right? If you're interested in getting twice as much charge and twice as much energy on there, why don't you charge it with an 18-volt battery instead of a 9-volt battery? Well, sure, you could do that if you have an 18-volt battery. But guess what? When you take that capacitor out and you plug it into something, it's also going to apply 18 volts, and it might fry whatever you're doing. You don't necessarily want, in exchange for storing all this energy and charge, to have all this voltage coming along with it. So if, this is the kind of consideration if you work at Duracell, right? You're not trying to, you don't, if someone wants to buy a 9-volt battery, you say, here's an 18-volt battery instead, right? That's just rude, okay? What you do is you say, this is a 9-volt battery, but it's very long lasting, right? It's got a lot of charge and a lot of energy for that amount, right? So that's what the dielectric allows you to do. It allows you to store more charge and more energy at a given voltage. And again, the better your dielectric is, the more it's going to suppress the voltage between. And if it suppresses the voltage in between, then to climb up to the same final eventual charging voltage, you've got all this charge and all this energy before you get up to the end of the line. And just in full disclosure, this is hopefully instructive in the conceptual aspect. No one would ever do this. No one would ever charge up a capacitor, take it out, put in a dielectric, and then charge it up again. Okay? When you buy a capacitor, the dielectric's already in there. When you read the side and it says it's so and so many farads, it's including this value already. Okay? What you should do when you plug it in, you just go straight up to this. Right? you go straight up to this more charge and more energy than you could have stored without that being part of the physical construction. Okay? So it's kind of the unsung hero, right? When you're reading that capacitance off the side, it's already including the dielectric, and it can increase the storage ability of that many-fold, right? Remember, it gets increased by a factor of kappa, right? So if your kappa is 1,000, your capacitor is 1,000 times better than it would have been previously, okay? So in reality, you just plug it in with the dielectric already in there and go straight up to these values. Okay, so there's one more catch, and in the minute that I have remaining, I'm going to hint at that. So here's our dielectric. These are the things that make it better, or these are the things that these are the aspects of the physical construction that affect how good or not good it is. So if we want to have the best capacitor possible, we want to find the largest dielectric constant. We want to make the area as big as possible, and we want to make the plate separation as small as possible. These things will all lead to a larger capacitance. So, larger kappa value. Well, you're going to have to find a material that has that. If you can't find a naturally occurring material with a large kappa, you may manufacture one. But that you're inherently limited by the material available. Why might there be a downside to making the plate area larger?
Limited space.
It gets, if you have to carry it in the room with 2 hands, it's not going to be very practical. So there's your limitations here. It's going to make it bigger. It's going to make it a bigger capacitor. They've gotten around this problem too. Guess what? Some capacitors, when you crack them open, one plate looks like this, and the other one looks like this. It's a tremendous amount of area folded up into a small volume, kind of like a fractal shape. Okay, these are called electrolytics. You can get these tiny little capacitors you can hold in your hand, and the amount of area, if you unrolled it all, would be tremendous. The last one, though, this one's the most intriguing one. We'll pick this up next time. This seems like a win-win. Smaller is better, right? You put the plates closer together, it makes it better. So that doesn't seem like a limitation. That seems like a good thing. But as always, there's a catch, okay? So you can bring the plates closer together and you'll make it better until something happens. And that something is called dielectric breakdown, which is what we'll do first thing on Thursday before we move on to series and parallel caps and finish off the material for your exam. Okay, so that's it for today.